It's my great pleasure to welcome you all to our DSS series. This is the Distinguished Seminar Series in honor of Professor Cheng Mei, who's faculty in Civil Environmental Engineering, in honor of his contribution in both mechanics and fluid mechanics. So the goal of the series is to bring stellar speakers and researchers from around the world and to basically bring together the CE, MIT, and the broader scientific community at MIT for these basically broad lectures. For the talks, I would like to point out the website, dss.mit.edu, where the whole history of the series and also the recordings are there in case you're interested to see this talk again or to access the prior talks of the series. So today, we are honored to host Professor Sébastien Candel, Dr. Candel, can I say Candel? Candel? Candel, all right, Candel is a university professor emeritus at Central Supélec, Université Paris-Saclay, an honorary professor at the Institut Universitaire de France. He obtained an engineering degree from École Centrale Paris, a PhD from Caltech, and doctorate in science from UPMC, University Paris 6. Many of his research contributions have been in turbulent combustion, combustion dynamics analysis, modeling and simulation, combustion control, and cryogenic combustion under transcritical conditions and high-performance simulation with application to aerospace propulsion and energy. Among many distinctions, Dr. Candel has been the recipient of the Silver Medal of CNRS, the Marcel Dassault Grand Prix of the French Academy of Science, the Distinguished Alumni Award of the Caltech, the Silver and Gold Medal, both from the Combustion Institute. Dr. Candel is a member of the French Academy of Science, and he was actually the president of the French Academy of Science for the past 2 years. He's a founding member of the French Academy of Technologies and a foreign member of the National Academy of Engineering of the United States. So without further ado, please join me in welcoming Professor Sébastien Candel.
Thank you very much, Professor Bouriba. It's a real pleasure to be here. Let me tell you that MIT, viewed from France, is very high on the scale, probably the top-level institution in the world for the French. So to have in my curriculum the fact that I gave a seminar at MIT is very important. So as soon as I got this invitation, I could not say no. And besides, I was not anymore the president of the Académie des Sciences, so I said yes. And thank you again for inviting me. It's also a pleasure to be here because we have friends at MIT, Ed Greitzer, who is just sitting here, and Gang Cheng, who was actually a professor in our lab for a few weeks or months, and Ahmed Gonyem, who we meet very often at the Combustion Symposium, Franco Tamanini, who is working at Factory Mutual. He knows everything about fire and explosions and well, things which are very closely related to civil engineering. And let me tell you also that C.C. May, this distinguished lecture is given in his honor, actually has the same root as myself. We have both a PhD from Caltech. So it's a pleasure to be here. He has some very nice books on ocean waves and the theory and applications of ocean waves. So it's an opportunity to tell you a little bit about combustion. And of course, who is in civil engineering here? Raise your hands among the students. So is combustion important for civil engineering? What do you think? Yes, it is important. So I have a slide. This night I was thinking, well, I'm giving combustion in civil engineering. So what is the relation? So this is the slide that I made up in my mind, and then I produced this morning. So one of the application of combustion is just to make cement. Cement is based on a combustion process. So without combustion, it would be very difficult to produce cement. So basically, cement, which is everywhere, is due to combustion. The second one is glass. Glass is a remarkable substance. It's unbelievable how beautiful that is and the properties of glass. And again, that's a combustion process. You can have it in various ways. In this case, it's oxy-fuel combustion, but you can produce it in a different way. And the third application of combustion in your field of civil engineering is fire. Fire is, you don't want to have fire in your buildings, so you should build things which do not catch fire, which are capable of sustaining fire, and structures which are fireproof or delay fires. And fire is very important. And again, it's a combustion process. Of course, it's a negative combustion process. So once I've said all that, you see that combustion is very important for you. But of course, I'm working in a different area. My area of research is more oriented towards aerospace, aeronautical propulsion, and space propulsion. So, but what we learn in one field is, of course, very useful in another field, in another application. You know, the basic principles are the same for all the previous applications. It's all the way that we use combustion that is different. The other thing to know is that 85% of the primary energy comes from combustion. At this point in time, most of our energy in the world is due to combustion. It uses a combustion process. In some applications, it is very difficult to replace combustion. For example, to fly an airplane, it's terribly difficult to do it otherwise. Of course, there is an airplane which flew with photovoltaic cells. You know solar impulse. The airplane made in a year 40,000 kilometers. So it was one passenger times 40,000 kilometers, 40,000 kilometers passenger. But at this point in time, the normal aviation does 6 billion passengers kilometers per year. The numbers are enormous. So you see the distance between doing that with an electric aircraft, one single passenger, and he had to not sleep for 3 nights because the plane was flying at 90 kilometers per hour. And so it's difficult. It's very difficult to have electric airplanes. For very short runs, you can, but not for transportation, at least not at this point. It's even more difficult to fly a rocket with something else than combustion. So combustion is very important if you want to have GPS, if you want to have satellites for communication, or if you want to have observation of the Earth. You need, again, rockets, and rockets, there is no other means of flying a rocket but combustion. So what I'm going to tell you is a little bit of historical perspectives in aeronautics and combustion, the key issues, very rapidly, and then give you some examples of our recent work that is essentially in the field of combustion dynamics. When you have a combustion process which is in a dynamical stage. Ignition, for example, is dynamic. We have combustion instabilities, that is the coupling between combustion process and acoustic modes that make something very special that can have very detrimental effects on the process, especially if it's done in a high-performance device. And so this subject of combustion instability coupled by acoustic modes is an important subject, and Ahmed Ghaniem has worked on that extensively, and of course we interact on this field. The other area which is very difficult also is to look at processes which take place in rockets, and there you have cryogenic fluids at very low temperature, very high pressure. We are in a special condition, and here it's again something of very great interest, very difficult to study, and we've done many advances in this field recently. So this is basically what I'm going to tell you. So in terms of aviation, aviation is very new. It's a little more than 100 years old, that's all. So you can see how much progress has been accomplished. Of course, our hero here is Blériot. Blériot was an engineer from École Centrale, from the school where I was trained and where I have been teaching. Blériot in 1909, on the 25th of July, crossed the English Channel. It was just 6 years after the Wright brothers' initial flight. He was able to cross the Channel. He was the first. He got the Daily Mail prize, and that was a very big event. So this is the Blériot 11 flying again in Le Bourget 100 years later. So you see that plane. And this is the progress that has been accomplished. His engine. So why was he able to cross the Channel? Because he had the best engines of the time. The engines in France had double the performance of the engines elsewhere. They had, what is the performance? The amount of power per unit volume. And these engines were twice as good as anybody's engines at that time. So the engine is really the important part of an airplane. You see here the engines of the A380. These are very beautiful technology devices. And what you see here is that 18 kilowatts in the engine of Blériot, and now we are at 100 megawatts in these engines at full power. So you see the distance that has been accomplished here. And of course, you can transport up to 600, 700 passengers in this engine, in this airplane. Now, also something to notice is the power density, 1 gigawatt per cubic meter. So 1 cubic meter of combustion chamber is like a nuclear power plant. You don't have a cubic meter, you have less than that. But it's already a very, very strong, very, very dense. So there has been a lot of progress in these aircraft engines, especially what is progress, of course, to diminish the consumption. You want to have the lowest possible specific fuel consumption, the SFC, and you see that as years go by, we have been increasing the bypass ratio. The bypass ratio is the amount of air that goes through this secondary flow, through this secondary channel, divided by the amount of air that goes through the engine itself. And you see that we've gone to higher bypass ratios. This has been the trend. And as a consequence, you increase the propulsion efficiency, and this increases your global efficiency, and you get a lower fuel consumption. And in addition, you get a better, the noise level is diminished. It's for one time, you have the two things at the same time. Lower noise and as well as lower consumption. And this is reflected in the fleet. The fleet itself is much more efficient than it used to be. You see that as we change the airplanes, you change the level, the efficiency per passenger kilometer. You take the passenger, multiply by the kilometers, and measure the energy that you need for that. So E divided by RPK, revenue passenger, because you have also some passengers which do not give you any revenue. The pilot doesn't give you a revenue. So, but the revenue passengers, the people who pay, so you take the number, you multiply by the kilometers, and you see the trend is being reduced. You brought that to a much lower level. And of course, this is due to the fact that you improve the aerodynamics, you reduce the mass of the structure, and for civil engineers, it's always important to reduce the structure, the mass of a structure. But of course, we don't produce airplanes with concrete. You know, you would not be able to fly a concrete airplane. So you have to fly something which is really light. Yeah. And so you optimize that, and by optimizing aerodynamics, the engine and the structure, you can gain this make such a very large gain. And if you translate the number that you get, 1.5 megajoules per revenue passenger per kilometer, you translate that into, in our country, it's liters per 100 kilometers per passenger. And you see, you do 4 liters per passenger kilometer, per 100 kilometer. So that's very good. It's like, it's better than a car. This airplane flies at 900 kilometers, and still the consumption is less than a standard car, especially if it's an American car, which are not as efficient as, well, anyway. So 50 miles per times revenue passenger per gallon. So 50 miles per gallon. Suppose you are in a car and you make 50 miles per gallon. Can you do that? No. So the airplane does it. It's amazing. This is because technology has advanced so much, because what you've seen, these engines have been have evolved so much. Now, let me go to combustion. Combustion is something that has actually helped civilization. Without combustion, you think civilization would have occurred? Probably not. But man was able to master fire about 500,000 years ago. It took a lot of time to understand how to control combustion and especially do ignition. Ignition is only dating back, so some people say 30,000 years ago, some people 80,000 years ago. So ignition was controlled around that time. But the understanding of combustion is based on chemistry. You need to know chemistry. And chemistry was not there before Lavoisier. Lavoisier is the founder of modern chemistry. He was a member of the French Academy of Science, and he founded modern chemistry using actually combustion experiments. He was doing combustion experiments to understand chemistry, and he's one of the founders of chemistry. And it took a little more time to do the first theory of flames. It's based on the work of Maillard and Le Chatelier. This dates back to 1870. And they were interested in the explosions in mines. And they did the first theory of flames. The basic theory of flames is due to these people, and also Berthelot and Vieille were doing experiments. So it's these 4 people, and basically the initial theory of flames dates back to a little more than 100 years, 150 years. And then a lot of people worked on these problems, and there was a lot of theoretical work. Chapman and Jouguet on detonations, and Zeldovich and Frank Kamenetsky and John von Neumann. And von Karman was also working on that. And so during this period, a lot of theoretical work was done. And then the recent period is here. The little photograph here shows the picnic. We have every 2 years, we have a combustion symposium, and there is a social event, and it's a picnic. And this picnic took place in front of the Chambord Castle in France. A helicopter came in and took the picture. That's the only time where the combustion symposium was filmed. And this gives you an idea of the amount of scientists working in combustion. It's not very large. It's just to tell you, for example, in astrophysics, you have 10,000 of people working in this field. And in some other fields, it's even more. In combustion, it's a small community. This includes the ladies and the kids. Everybody's there. Yeah, so it's a nice field because you don't have such a competition. In a sense, it's nice. So what is now the situation? The situation is that we have these 4 blocks. Theory is still very important, and we do theory. We are guided by theory. We always work on theory, but we won't see any equation here. I thought I would not impose an equation to you. Simulations have gone very far now. We are doing parallel computing, high-performance simulation, and this has opened the horizon. It is now possible to get answers, calculations, solutions in just a few weeks, while with previous hardware, it would take 100 years to get one solution. We will see that. Experiments, they have also advanced tremendously. When I started, it wasn't like that at all. And now we have lasers, cameras, very high-speed cameras. We use optical diagnostics. We can combine these diagnostics with the signals. We do data processing. It's been a long time since we've used very heavy, very massive data. It's not just last year. It's many years ago, we started looking at data and learning from data. And of course, all of this is in conversation. So we try to do theory, experiments, data collection and processing, and simulations, all at the same time, because the problem is difficult. Because it is difficult because it's a combination of many disciplines. So you have to learn not only the fluid mechanics, this is our background, that's your background as well, but you have to learn about the chemical kinetics, and it's a complicated kinetics. You have to learn about thermodynamics because many cases you have different phases. The situations are very high pressure, so you have real gases take behavior. And we have transport plays a big role. So multi-species transport and how the molecules finally get together and react. So these are at least some of the disciplines. In addition, you need to know a little bit of quantum mechanics because you are using lasers, because you are using spectroscopy, things that are not the standard mechanical engineer or civil engineer habit, but you need that. You need to know what happens if you do experiments. You have to learn that. And then computation as well. So when you're doing combustion, you're multidisciplinary. You don't have to wait people to tell you, yes, you should be multidisciplinary. You are. You need to know all that. And now we have, you accumulate all the difficulties of all these fields. For example, you have these complex kinetics, which are governed by Arrhenius laws. You learn about these laws. They are exponential with temperature, and as a consequence, the problems are stiff mathematically. You have a stiff problem. You have the flow is turbulent. In most applications, the flow is turbulent. So again, it's difficult. You have critical conditions, ignition, extinction. Sometimes the flames exist and sometimes they don't. And then you have coupling, for example, with radiation. So heat is radiated. And this is what you sense when you have a fire in your close to you. You feel the heat coming in. And in addition, you can couple with acoustics. So that's a big problem because if it's coupling, you can bring the system to very high level of oscillation, and that may not be good to your system because of vibrations and reduction of life cycle. So we have to cope with many problems here. Now, on the theoretical side, for example, in the 1954, so the pictures don't correspond to 1954. Carmen is very young and Penner is old here. I just put two pictures just to tell you that. So this work was done on a flame which has two reactions. One reaction is ozone with one molecule gives oxygen and molecular oxygen, and the other one is oxygen plus ozone gives 2O2. It's a flame. It's a very special flame because you don't think you can make a flame from ozone, but you do. But it's two reactions, and it takes about 15 pages of calculations by these two people. And they say that this method probably will be able to cope with more complicated hydrocarbons, with larger mechanisms. These were just two reactions. But in fact, this is not how we did it. We are now able to cope with such mechanisms. This is, for example, the mechanism for hydrogen. It's 38 reactions and 9 species. So if you want to do a calculation of a hydrogen flame, In fact, you have to use these various reactions and all the pre-exponential factors and the activation energies, and you have to cope with that. And in addition, the problem is mathematically difficult, but we know how to do that. Why? Because we use computers. We now use a computer to handle all these reactions. You are not coding by hand the source terms. You are using a processor which will code for you the reaction terms, which will provide the thermodynamics, which will allow you to actually calculate such flames. So we learned that. The other big problem in combustion is that all these flows are turbulent. For example, you see this is the flow in a glass furnace. So that's for civil engineering, it's important. Glass, how would you make a building without glass? You know, all these buildings, the new buildings are just made of glass, and this comes from combustion. So, so turbulence is difficult, but in addition, because of combustion, you have all the scales that are related to kinetics, that are related to the combustion process that you have to take into account. And it complicates the situation. In addition, the flows are swirling. That's a complicated situation again. And the fuel may be a spray. And this is, you know about sprays a lot in a very different field. And then you have complicated boundary conditions as well. So you must be really bold to work on such problems. So in combustion, we have to work on difficult, multidisciplinary, multi-physics problems. And how do we do that? Of course, without the computer, it would be more or less hopeless. You cannot represent such complexities by hand. Of course, you learn a lot from simple problems, but when it comes to calculate something, you need the computer. For many years, we were using the Reynolds average equations. You take the Navier-Stokes equations and you average them and you calculate with this Reynolds average, but you need a lot of modeling, and that's difficult. And then we started doing direct simulation. You take the equations, you put all the chemical terms, and you do a calculation from scratch. And this is possible. You take into account all the scales, the small scales, the big scales, all the time scales, everything. It's possible, but you can only work on very small problems. Because you can show that the resources required grow like the Reynolds number to the 9/4. So it goes very fast as you increase the Reynolds number. And in the middle, you have larger dissimulation. So this is what is being used, for example, to predict the weather. And the predictions are very good. Usually, at least in France, the weather is predicted with an extremely good capacity. And here, I'm sure it is also. You have, for example, yesterday, I didn't believe it would rain today, but it was predicted and it rained. Yeah, so LES is great. And you see you can calculate. So what you calculate in the LES is the large scales. In direct simulation, you try to calculate all the scales in the spectrum. In LES, you say the large scales are calculated and the small scales are modeled. So this is the principle. It's a simple principle. You think that at the small scales, it's more or less universal. At the large scale, it is not. So you calculate the large scales and simulate and model the small scales. This is called the subgrid modeling. And now, why is it important? Because you can start thinking really to calculate flows of practical interest. For example, in the combustor, in the engine. You see the combustor is really small. It's a very small device right here. All the power, without that, nothing works. Yeah, you need the combustion here so that it works. And in the engine here, this is a rocket engine. You have 500 injectors. In these car engines, which are using all day long, you have also complicated situations, the geometry. This is a direct injection engine. This is a gas turbine. Again, you have a complicated situation here, and that's another diesel engine. So in all these devices, it is now possible to do LES. And the thing has started in the 1990s. It took a little while to do combustion LES. What was done before was just fluid mechanics. And combustion came into being a little later because it's more difficult. So we started, our first paper in that is 98. We began really to do nice LES. Of course, you've been doing some of LES even before that, but basically this field has grown around that period. And now we are like for about 200 papers per year in combustion LES, much more in fluid mechanics. But it's a growing field. Whoops. Yeah, the one difficulty in combustion is that you have the flame is very thin. The flame is typically of the order of a few tenths of a millimeter. And then you have a grid, and it's difficult to have grids which are extremely well resolved. So you have the problem of accommodating a flame on a coarse grid. It's a very fine grid in general, 10 million, 100 million of cells, but nevertheless, it's too coarse for the flame, so that's a big difficulty, and we worked on that, and some initial trials, one of the first way to do that is to thicken artificially the flame. So instead of having a flame which is very thin, you thicken that artificially while preserving the velocity. And this is some of the first examples of that. So you can see that the flame is, at the bottom you have the heat release, and at the top it's blue, it's fresh gases, and red is burned gases. And you see that the flame is distorted by the flow. It's a turbulent flow. You can see pockets which are burning, and you see that it's already something useful. You can calculate something which looks realistic. It's a flame. It's in a model combustor. That was around the year 2000. And now we are in much better shape. For example, this is a swirling injector. So the flow is swirling, and the flame is stabilized by recirculation inside this region here. And you see that you can calculate such flames very nicely. And you can actually compare some of the species that we measure, for example, with fluorescence, with the calculations, and the agreement is reasonable. So now we get to points where you have a grid with 40 million cells. It takes about 200,000 CPU hours. But you get a restitution in a week because you distribute that over 2,000 processors. How many hours in a year? Who knows the exact number? Do you know how many? 5,000? 9,000? 8,760. So you see, a year is not so long, unfortunately. And how would you get these hours if it was on a single processor? You would never be able to do that. So now we go from, much of the work has been done in labs on simple flames. One single flame, isolated, you do the measurements on such flames, like this one. This is a swirling flame in our lab. And more recently, we started doing things which look like aircraft engine combustors. What you see here is what we call Mica, and this has 16 injectors. In this case, these were pre-mixed propane and air, and all these flames are stabilized by swirl. The swirl is used in industry for flame stabilization. Of course, you initiate with a spark plug. And once you have initiated that, the process is there. So at the beginning, this was engineered to study instabilities, how the flames interact with the modes, especially azimuthal modes. And we didn't get any instability. So we decided, let's look at ignition. And this is what we started doing. So again, this is the aircraft engine, for example, the CFM56 produced by Safran and General Electric. And you have the annular combustor is sitting here. Of course, you cannot do any experiments on this combustor. And this is our laboratory scale combustor. You see the walls are made of quartz. We have 16 injectors, a plenum, which feeds these injectors. And the geometry is annular. In this case, it's premixed propane and air, atmospheric pressure. Of course, that operates at high pressure, but at ignition, it's at near atmospheric pressure. And more recently, this has been transformed into mica spray, where each injector injects a spray. So here we get closer to the aeronautical situation. It's still atmospheric, because as you go to higher pressure, it becomes more expensive, more difficult, but you have to learn a lot at this point at atmospheric pressure. So let me show you first an ignition. So here it is. Yeah. So what you see here is in false colors. The whole process doesn't take much time. It's about 50 milliseconds. But of course, it's at low speed now. And you see that each of these injectors are ignited, and then the two flames are merging. And finally, you have each of these injectors which are operating. So the problem here was to see if we could actually represent that process numerically. So we started a new student working on a PhD just to try to represent what is seen here numerically. And this is what comes out. So what is plotted here is on the left side, it's the experiment. It's light emission intensity. You can think that this is somewhat like the heat release. And on the right, we just show the flame surface, and it's one of it's like a temperature surface, a constant temperature surface, and it's plotted to make it more visible. You show on the surface the actual velocity. So you have something which is more complicated. So the two things are not quite the same, but basically you can compare them nevertheless. So the experiment is, it's red because it's false colors. It's nothing, it's a blue flame. But you can see that the structures are very close. And the merging time is very good. Even the structure, this is turbulent. This is a really turbulent flow. Nevertheless, you have something which is very realistic, yes? You can see it again, yeah. So now such a calculation is 1,000,000 hours. You need 1,000,000 hours of CPU time, so you cannot do such calculations all the time. You have a certain amount of computational resources. And at the first try was this one. So you get a good result without having to change anything. Just using the right models, using a good LES code developed at Fairfax by the team of Thierry Poinceau. And you see that definitely it is possible to retrieve this situation quite well. The thesis student was Maxime Philippe, but we were a number of people to help him do that, doing experiments and calculations and discussing this. So this was rather successful. And in terms of, you see the delay for the merging of the two flames, the LES is here, and this is the data. So you have to match the boundary conditions of the calculations with the boundary conditions of the experiments. It's not so easy. In fact, you should do a calculation which takes into account the heat transfer and so on. So what we did is to preheat the walls and do the calculations using adiabatic walls. So it's more or less, it's not quite the same, but it works. So now what we've done more recently is to actually have that done with sprays. So we compare, on the left, it's premixed air and propane. In the middle, it's heptane and air, and dodecane and air on the right. So what you expect is that the fastest will be at the left, and the slowest will be this. And it's true, it works. So you see that the premixed is faster, and this is slower, and that's slower. Yeah, it's just the second time. So the idea is then, we've been able to do that in the premix case. What about the spray case? Is it possible to actually calculate that? And here we had another student working on that, Théa Lancien, a young lady, and she has done these calculations. And again, it's not too bad. This is a much more complicated process. The spray description is very difficult. So you have to actually, in this case, we use an Eulerian representation of the spray. But basically, it works well, again. And in terms of delay, this one is very good. You know, when we are at a global equivalence ratio of 0.79. This one is very, very good as well. And this one is not. So there is still work to do. It's not perfect. Why is it that when we approach the stoichiometric conditions, it's not too good? Anyway, the combustors usually work in the lean regime. So in this region, we are fine. But still, there is work to do. We haven't completely solved the problem. Let me now turn to this combustion instability, because all that was done to study instabilities coupled by modes which are azimuthal. And finally we got these instabilities. At first we were not able, but we learned how to build injectors which could become unstable. So you have a learning process, and by doing that, then you know how to make something which doesn't go in the right direction. It's interesting. And the first film is to show you one of these instabilities. So what you are going to see is the mica burner. So let's go back. Oops. So we study these azimuthal instabilities. They are coupled by modes which are either rotating or fixed, but azimuthal. So in this case, instead of the swirling injectors, we placed matrix burners to have a laminar-like combustion. So in this case, we eliminate the problem of turbulence. And so this is the instability that you hear. It's much stronger in the lab than here. And this is what you see at slow speed. You see that the flames are continuously, there is a rotation here. This goes more or less like the speed of sound. And then we have a standing mode. And in this case, what you have are flames on one side, and then on the other side, you see the heat release is increasing on one side, on the other side, and it moves like that. There is a nodal line in the middle. And then there is a special mode which looks like a stadium, you know, where people go up and down, you know, all together and it's the slanted mode. It's a strange, do you have that here in some stadium, in football stadium? You see, it has a strange, in fact, it's a mixing of two modes here. So we studied that experimentally. And of course, you want to be a little more quantitative, and it is possible by using multiple microphones. You can watch the microphones with respect to themselves, and this is a stunning mode. You can calculate a spin ratio and say, yes, this is a mode which is fixed in space. And then, so you have on one side red and the other side blue, and then the thing is changing. And you can see it even in this case, where you have essentially a nodal line in the middle, in the diameter, and on this side it becomes blue, when on that side it's red, and vice versa. So now we have a system where we can study these azimuthal modes and the coupling between combustion and azimuthal modes. This is a rotating mode. You see the microphones are very different here. You have this, it looks like a wave. It's true, it's a rotation. It's a wave which rotates around the azimuth. And it's a mode which moves like that. It rotates here. So these are possibilities in engines which have this annular configuration. Why is it important? Because the largest size is the perimeter, and so the frequency corresponding to that is the lowest, and it falls into the region where the flames are most susceptible to instabilities. And this is why we study these modes which are azimuthal. All right, so let's, and that's another situation of interest. The instability will arise and will be so strong that some flames are actually extinguished. You see? So actually, our student here got one of the prizes in Europe, the Clean Sky Prize, for this work, and he's shown here, Kevin Prieur. And this is what happens when the amplitude of oscillation reaches about 5,000 pascals. The flames are extinguished in the middle by these very strong oscillations. It happens around the nodal line, the pressure nodal line, where the velocity, the transverse velocity, is highest, and you have this extinction. So it's a very interesting process. You have combustion, which is the flames are blown off due to the combustion process. All right, so let's now move a little bit to space propulsion, because you have similar problems here. They are even more difficult because everything works at very high pressure. So in an engine like this one, this is the Vulcain engine of the Ariane rocket, the pressure is 110 bars. It's twice the critical pressure of oxygen. And you know, the critical pressure, if you are beyond that, there is no more interface between gas and liquid. This has disappeared. So there is no atomization, no fragmentation. It's all different. And we wanted to know how that works. The power density is 50 gigawatts per cubic meter. So one rocket engine, it doesn't have a cubic meter, but if you have a cubic meter of such an engine, you produce like 50 power plants. It's a very large, and this is a small engine. It's not even a big engine. So, and here, how does that look like? Well, you have many injectors, typically 500 injectors, which form the backplane of the engine. And what is interesting is that the hydrogen flows at 200 meters per second, very high speed. So how is the flame stabilized in a situation like that, where you have such a very high speed flow? And that was an initial mystery. How is the flame stabilized in this case? And also, whenever I take a shower, I think about the rocket engine. It's unfortunately, it's impossible. Yeah. So So it looks like that. But in fact, here you have coaxial injectors, hydrogen and liquid oxygen here. The liquid oxygen is injected at a few meters per second. And what happens is that we are above the critical point. So we start from a situation where the temperature is low, but the pressure is high, and we move essentially at constant pressure. So this is on the test bench. This is the test bench. And this is in the Ariane rocket. So basically here you have oxygen, which has the density of water. And then as it moves, as the temperature is increasing, its density diminishes, but you don't have any liquid-gas interface. And this can be seen in these experiments. You see here, this is at low pressure. You have here nitrogen, liquid nitrogen surrounded by helium, and you see droplets being formed and the initial breakup and then atomization and finally vaporization. But if you are at high pressure, like here, again it's nitrogen surrounded by helium, you don't see anymore the droplets. There are no droplets. The mass transfer takes place through a diffuse turbulent interface. So we wanted to actually calculate something like that. And of course, this took a lot of effort. We did experiments on small combustors with a single injector, and then we did calculations here using LES. And so let me show you first the experiment. Yeah. This is ignition, and then the pressure increases, and now we are stabilized at about 56 bars. This is methane and oxygen. So this is how the flame looks like. And oops. And the calculations are here, if I can run them. Yeah. And if you remember the flames, it looks very much the same. The length of the flame is well represented, so the heat release is properly represented. And now this is a calculation which is done under transcritical conditions, turbulent, high pressure, reactive, and it represents what we've seen experimentally. So we were very happy with that. So that's a rather recent result. And then we did more experiments. Of course, rockets have also these very, very problematic instabilities. And one way to study that was to make something which would look like a small engine with 5 injectors, not 500, just 5. And we would place 2 nozzles. Usually you have a single nozzle. Here we have 2 nozzles, and we block the nozzles alternatively. So you have this device. I have a film here. We call that the very high amplitude modulator. And you see it blocks one nozzle and then the other. And like that, you have an acoustic source, and you can trigger the transverse acoustic mode. And you can get levels inside the chamber of more than 210 decibels, which is a world record of the level of decibels. I don't think you can do it. So you get a very strong transverse oscillation. Now, of course, you want always to do the calculations of what you are doing experimentally. This is a complicated situation because this is the chamber. You have the 2 nozzles. You have to represent this blocking of the nozzles alternatively. So you see the number of elements. It's about 60,000 elements. And this is without any oscillation. So these are the jets. We have 5 jets here representing a larger number just to see how it works. And now this is what happens under experiments. The jets are initially on the left. You have jets which are under natural conditions, no oscillations. And on the right, the oscillation is there. And the jets are much more compact. So the acoustics here, this coupling with acoustics, makes the jets much more compact. Does the calculation do the same? Well, first of all, you have to check that you get the same modes in the experiments and in the calculation, and this is correct. And this is the calculation. So the jets are more compact. So you represent this effect which has been seen in the experiment. Not with the asymmetry that was seen in the experiment, but the jets are indeed more compact, and they respond to this very strong acoustic motion, transverse acoustic motion. And the more recent stuff is that we've been able actually to look at something which looks like a rocket engine with 42 injectors and which has features, instabilities. And you see a calculation of this situation that's a lot more difficult because you have this complex geometry, but it's all modeled in this calculation and here. And you get something which is, when you analyze the signals, and we've looked at the modes and so on, it's pretty reasonable. You see the spectra, the power spectral density from the simulation. The resolution cannot be as good as in the experiment. In the experiment, you have sufficient time to get the data and to do the averaging and so on. In the calculation, it costs too much. So, but basically, you get the two modes. This instability is coupled by two modes and not a single mode, and it's pretty close to what you see experimentally. So that was a very difficult problem, you know, during the Saturn V development. Combustion instabilities, high frequency instabilities were a big problem. It took a lot of effort to solve them before the rocket could be launched. And now we are getting closer to predicting using LES. So there has been a lot of progress. We are now really closer to understanding and to actually representing these mechanisms. So this is my last slide. I just wanted to tell you that we've made a lot of progress in combustion dynamics. And this came from experiments, from calculations, from theory. We have combined all that. It's, if you do just calculations, you're not capable of representing. You need to be guided by experiments. Without that guidance, it's very hard to. And of course, our asset is that we do experiments and we do the calculations as well. Many students in our group actually do the two things. I don't know how they do it, but they do both. And there are still many intriguing phenomena. It's not fully solved. So you have here the best part of it, but there are many problems yet to look at. So it's. The situation is fine, but there are many difficult problems. Like, for example, soot in production in flames is a very difficult problem, and we are actually engaged in trying to solve that problem. And there are many other aspects which are not fully understood. There are many features which need more work. So with that, that's my conclusion. Thank you for coming and for your attention. Thank you. At Greitzer.
Very impressive array. It's a very impressive array of experiments and computations. And I guess this is a question about these progresses versus challenges. You've captured a number of different features with the computations that you couldn't have done 20 years ago,
no.
Or maybe even 10 years ago. So are there more features to capture, or have you got most of the features and the rest is quantitative improvements? Or where are you in this process?
Yes, some of the, yes.
Is that a
yes.
fair question?
Yes, yes, very good. Yeah, yes. Yeah, we are very happy with many of the features that we captured here. For example, it's difficult to think that we could calculate these high pressure flows because you have to actually use real gas equation of flow, it's equation of state, which is not very usual. You use always P is equal to rho RT, the perfect gas. And here we use real gas. And we use real transport features, which are, again, a whole problem. And we tested that first on very simple flames, counterflow flames. And so some of the features are great because before that, but what we didn't have was even a single experiment on one single transcritical flame. This came out in the 1990s up to the year 2005. We did all this work on cryogenic combustion. Why did we do that? Because engineers always know how to make things without full understanding. You make an engine, it works, you improve it by testing, but to understand how it goes, for example, how is the flame stabilized in this very high speed flow? We needed that experiments. The drawings, we had a panel working on this problem, and what people were drawing is not what we finally got. They were thinking that the flame was lifted at a distance from the injector. It isn't. It's stuck on the nose of the injector, and it's not a lifted flame. And so using experiments, you see, you are guided by that. And afterwards, there was this problem of representing this complicated physics, the real gas effects, the high pressure, the LES, how you accommodate the flame on a coarse grid. All these had to be done. So we are in pretty good shape. We do also complex chemistry, so we can calculate rather simple pollutants, not as well as we should do. For example, CO is not very well calculated. And as you go, if you want to calculate soot, that's difficult because the process is so physically complex that we are not yet there. But we are. This is one goal, is to be able to calculate soot from basic principles. So you see that there are challenges, but it is true that some big challenges are now, you know, such calculations, these LES calculations are done now routinely in the companies. You know, the Safran is using LES to calculate combustors, which wasn't the case for many years. Industry was using just RANs. And now they use LES. LES is now used by industry, and engineers are calculating flows using LES. And so that's a big advance. And it's the same code. The same code that we use for research is used in engineering applications. So now still there are many things. I've shown what works. I've shown also that certain points don't work. For example, the treatment of sprays is always difficult. So this is why you are working on sprays, essentially. It's different sprays, but that's a difficult problem. Sprays and pollutants and soot, these are difficult problems. Yeah. Give the microphone to him.
So I suspect that when you went from the lean to the almost stoichiometric, slightly richer flame, things didn't work as well because the chemistry. Most likely the kinetics were not as...
Perhaps the chemistry, perhaps the flames now are spray flames. So you have something also pertaining to the spray. Maybe it's not well represented, yes.
My question is, if you're hoping to get the multi-injector transcritical at pressure,
Yes.
it will be a lot more difficult because
No,
the
but-
chemistry there is a
Yeah,
lot more.
for the case, for the rocket case, we got it. We got even the coupling with azimuthal modes, and these papers in Combustion Flame correspond to that. And also we gave a paper at the symposium. We are able to calculate multiple injectors, 42 injectors. Each injector has to be, of course, discretized, and you need to have a very large number of cells for that, very, very large number of nodes. But basically, you do get the oscillations, the two modes that are found experimentally are obtained just from the calculation. So it's not yet routine. It's still a lot of work, and you cannot give that to an engineer, a standard engineer. It's still, but we get closer to that. Yes. Just in the back there.
Great talk, Professor. I was wondering on the Mica combustor, it looks like it was running stably in some conditions, and then once the walls reached a certain level of preheating, it became unstable.
Yes.
Do you have any idea what the pathway for that is?
Yeah. That's a very good remark. The system is stable when it's cold, which in general we think it's the other way. You should be unstable under cold condition because the flames are not very stable, and yeah, it's the other way. As the walls get warmer, it becomes unstable. It's strange, and probably what happens is that the way the flames are stabilized change. Because you have heated walls, you get more possibilities to stabilize an outer flame, and these are more susceptible to oscillations. So it's a matter of changing a slight change. So this is why combustion instabilities are so difficult. It's because they arrive always. There is something unusual. It's not. We little by little get a better understanding, because at first we were very disappointed. There were no instabilities, no azimuthal instabilities. So we had to engineer the injector to become unstable. So that's why we did all the ignition studies, because we were not supposed to do any ignition studies. This was a different group. So, but what do you do when the thing doesn't work? The student has to get something. So we did. So that's how we got. And in the meantime, this allowed us to test various possibilities, and like that. And now we have a number of injectors, and for example, the 716 is unstable, very unstable, brings very high level of oscillations. So one reviewer was telling us, yes, but you will never have such a very unstable situation. The engine will be shut before. Well, if you're in an aircraft and you shut the engine because it becomes unstable, that's very bad. So. And he was saying, you have 5,000 pascals. It's too much. It's 5%. So an engine would never feature that. Yes, but the possibility exists. And then the flames are extinguished. So we did a study of how these flames are extinguished. So, but one reviewer was saying it's useless because it will never get there. So. Anyway, fundamentally, it was interesting to study, so we studied that. Research is full of surprise. It's not always, you expect something and something different happens.
You look for the instability, you can never find it, and if you're not looking for it...
Yes, you find it. Yes, sometimes. But these are special. They are azimuthal. You need this rotating or these modes that I've shown here. Yes.
I have a question more on the applied side. So you mentioned instability mostly as a bad thing because it can shut the flame off. But you also had one example where you showed the flame is smaller.
Yes.
Thanks to instability. Like, are there any positive impact of instability?
In fact, what happens under unstable conditions is that the flames becomes more compact in rockets, and as a consequence, the heat fluxes to the walls are augmented, and the walls do not sustain that, and they melt. In just a few seconds, the engine is melted. When I was a very young engineer, the second flight of Ariane was a failure because of this instability. And I was in the committee searching for the reasons of that instability, and for the why did it melt, and we found that out. So these studies grew out of the necessity to understand what goes on, and that's a problem that has been with us for many years. For example, we were speaking about Tien, the rocket scientist who was a professor here and at Caltech and later in China, who did the Chinese rocket program. And Tien had been working in the 1940s on combustion instabilities. So the problem, but at that time, no computations, no knowledge of how the flames are operating. All of this is recent. Yeah.
So I'm always stretching in class the notion of scaling, dynamical similarity, and all of that. So here, for this experiment that have the instability with the changing modes, and
yes.
So the driving mechanism, I mean, the geometry is also probably very important, the spacing,
yes.
how all that is feedbacking the turbulence and the chemistry. So how do you then scale back all of this to the real system and be sure that the regimes of transitions are applicable, given all the parameter space that is involved?
Yeah, of course you cannot do such work on real configurations. So the real stuff is always difficult to actually study because the metal and even to put a single sensor is already a complicated problem. And in addition, each test will be very expensive. So what we learn from laboratory work is that on a simple system, we learn how it works. We can do experiments. This is basically two people running the experiment. So you can actually put a student and somebody else, at least two people, and you can run these experiments repetitively. It doesn't cost too much. You can change things. You can, for example, say, well, I want a chamber which is longer than this one. I want this. I want, and so it allows you to do all these parameter space studies. For example, we started looking at the effect of the head loss across the injectors. So you design injectors which have the same swirl number, so they give the same rotation, but have a different head loss. And then we looked at the instabilities of such injectors that you cannot do on a practical system. Then you use the calculations and you try to match what is done experimentally using calculations. And if it matches, then you think that the calculation will allow you to look at more complex configurations. You can scale it up. So first of all, you learn a lot about, at first, we didn't know very much about swirling flows and how they work. And for example, during ignition, the flame, when the flame is moving, sweeping the injectors, it gets inside the injector. And after a little while, it's expelled. It goes outside. So we didn't know that, but we saw it in the experiment. And now we have some theoretical work on that and some calculations which are matching that. So of course, you don't want the flame to be inside the injector. It's a very short time, but it's sufficient to heat it up, and that's not good. So the experiments give you a lot of clues, and then you do calculations or you do theory, and this can be useful at a larger scale. And so That's, for example, the single injector experiments on the rocket engine situation. Again, before the data that we got, there was nothing to tell you that the flame was looking like that the size of the flame of that kind. The main parameters, the Weber number, the momentum flux ratio, it was not known. People didn't know. And actually, one of your collaborators, Emmanuel Villermo, worked with us on this problem of what is the effect of the momentum flux ratio on the size of the flame. So you learn. It's very interesting to get that information on a simpler configuration and transpose that to a more complex one. So I think I try to convince people that laboratory scale experiments are very useful. They don't cost much and you learn a lot. Big experiments, you cost a lot and you learn very, very little. So when you go smaller, usually you get more because of the parameters and so on. All of you know that. Yeah.
All right, on this note, with which I agree completely, let's thank the speaker one more time.
Thank you. Thanks.